Hello and welcome to this lecture. So far we've been looking at two random variables. Things seem maybe complicated enough even in the two variable world. We're going to go to more than two variables now. Okay, so 3, 4, 5, 6 and believe me, when you look at complicated problems there'll be hundreds of variables, so you should never be scared of multiple variables. So let's get used to some of it even in this course, right? So let's start thinking of more than two random variables. How do you think of all these PMFs? You know, still in the discrete world, joint PMF, marginal PMF, conditional PMF. How do you do all that? Is the beginning of this lecture. Okay. So actually, the joint PMF itself for multiple discrete random variables is very easy to define. Supposing you have n discrete random variables, x1, x2, xn, that are all defined in the same probability space, right? And every random variable will have its own range. I will call that Txi. Okay, I can do that. And then the joint PMF of all these guys, x1, x2 to xn, one can write as f subscript x1, x2 to xn, isn't it? Just like we did for before. We had two random variables, you put f subscript xy. You have n random variables, you put all of them in the subscript. And it will become a function from the Cartesian product of the ranges for each value that the random variables take, right? x1 takes some value, x2 takes some other value, xn takes some other value. For every possible value that each of these random variables can take. Let's say x1 takes value t1, x2 takes value t2, so on till xn takes value tn. What's going to be my joint PMF evaluated at t1 to tn? It's simply the probability that x1 equals t1 and x2 equals t2 and x3 equals t3, so on till xn equals tn. Okay, these ti's have to belong to that particular range, and that's just the joint PMF. So if you have a small enough example, you can write out a table. But we saw soon even in the example problems, quickly you will get into situations where you can't write tables and all that, and you have to keep the joint PMF and the picture of it, imagine it either as a plot or table or something in your head, and work with it in problems. Okay, so that is something important. Okay, and we'll use the same thing, this probability of x1 equals t1 and this and we will not repeat, we'll just put a comma, and you have to interpret it as and when you write it down. Okay, so this is joint PMF, easy enough to define, right? So let's see a few examples and make sure we understand it. Okay, so let's go to the example of the fair coin toss. We saw earlier the coin was tossed twice. Now we're going to toss it 3 times. So when you toss it 3 times, you naturally define 3 random variables, x1, x2, x3, and here this is small enough that you can write down a table. Okay, so if you write down a table of t1, t2, t3, they could take values 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. 8 possible values you can write, and notice how I've written these zeros and ones. It's very common to write them in this sequence, sort of like start with all zeros and then work your way towards all ones by flipping the last one, making it 0 to 1, etc. Okay, and every possibility, the joint PMF, the probability that the first toss is a tails. If you look at 0, 0, 0, the probability that first toss is a tails and second toss is a tails and third toss is a tails, right? That's half into half into half, 1 by 8. And any other case also, it's 1 by 8. The coin is fair, whether it's head or tails, probability is half. Anything happens, you just multiply half 3 times, you get 1 by 8. Okay, so there are 8 possibilities, each is 1 by 8. So sort of like the joint PMF is uniform in whatever range that you pick. Okay, simple example, easy example. So let's go to a slightly more complicated example. Okay, I'm going to define a 3-digit random number now. Okay, previously we had 2-digit random number, now we want to do more than 2, right? So we got a 3-digit random number, and we'll use this notation 000 to 999 to denote these 3-digit random numbers, so that we have around 1000 digits as opposed to say 900 digits or some 900 such numbers. We have 1000 numbers, 000 to 999. Okay, I'm going to define 3 random variables here, slightly maybe different from what we did before. X is the first digit from the left of the number, or the 100th place of the number. Z is the first digit from the right, or the units place in the number, and Y is the number modulo 2. Okay, so what is number modulo 2? If the number is even, it's going to be 0. If the number is odd, y is going to be 1. Okay, so that's the thing. Okay, the table is too long here. I mean, you can write down all the possible values here. X can take how many different values. Let's go to my color here. So x can take values, if you want to think of the range here, it can take values 0, 1, 2, so on till 9. What about y? Y can take values 0 and 1, and z can take values 0, 1, 2, so on till 9. Okay. So, if I have to write down the probability now, the joint distribution of f x y z, let us say of 0, 0, 0, what will I write down? This is the probability that number starts with 0 and number is even and number ends in 0. Okay. So, what are all the favorable cases? 0, 0, 0, 0, anything 0, right? 0, anything 0, number is definitely going to be even. It starts with 0, ends with 0, isn't it? So, how many such possibilities are there? 10 possibilities are there. So, that gives you 10 out of 1000, and that is 1 by 100. Is that okay? So, maybe you want to look at some other case which is a bit more interesting, maybe, I do not know, 1, 1, 1, let us say. Okay, what will happen to 1, 1, 1? It has to start with 1, okay, it has to end with 1, and it has to be an odd number. Okay, it is always going to be odd if it ends with 1. So, again this will be 1 by 100. What about this guy f x y z of, let us say, 1, 0, 1? Okay, it has to start with 1, end with 1, and it has to be even. That is really not going to happen. So, this will be 0. Okay. So, you will get these kind of possibilities. There will be this 1 by 100 showing up a lot, and you know, you can see why, right. So, if y is 0 and the last digit is even, you will get 1 by 100. If y is you know, y is 1 and the last digit is odd, you will again get 1 by 100. If y is 0 and the last digit is odd, you will get 0, and things like that. Okay, so you can see how the joint PMF can be written down. It's not a very particularly interesting exercise, but you can see how joint PMFs work through examples like this. You know, some interesting possibilities can happen for every possible case. You'll have to write it down. So if you want, you can just, let's just do one more example. If you think one more example will help you. f x y z of, let's say, 8, 0, 6, right? What is this going to be? It has to start with 8, end with 6, and then it has to be an even number. Whatever you put in the middle digit, it's going to be even, right? Because it's ending with 6. It's easy to do this. So, you'll again get 10 by 1000, which is 1 by 100. Okay. So you see what I mean. But if you do it the other way around, f x y z of 8, 1, 6, you will get 0. If it ends in 6, it can never be odd. Okay. So, it's a very easy joint PMF to write down. If you want, you can make a general rule about what it will be. Okay. So, if you say, you know, you can write like this if you like, right. So, you can do f x y z of t1, t2, t3 equals 0 if t2 is 0 and t3 is odd. Okay. And it is 0 if, okay, so maybe I should write the 0 here, 0 if t2 is 1 and t3 is even, it is 1 by 100 otherwise. Okay, if you want, you can write like this, and t1, t2, t3 take values in this. Okay, so if t2 is 0 and t3 is odd, then that cannot happen, so you get 0. If t2 is 1 and t3 is even, it cannot happen. In any other case, it will be 1 by 100, because there are 10 out of 1000 possibilities, and you get 1 by 100. Okay, all right. So that's the possibilities here. Okay, so sort of a strange example, but anyway, it's a good enough example. So let's go to our favorite third example here. Okay, so I just want to introduce a slightly more complicated situation where, you know, it's things are going to become a bit more complicated. I'll make a few comments on how to think of this. Okay, so let's take the power play over. Okay, so quite a complicated example. A lot of things can happen. And let's say the over has 6 deliveries. Okay, just to be sure. In fact, even that is not certain, isn't it? If there is a no ball that's bowled or a wide that's bowled, you can have 7 deliveries. But let's say the over had 6 deliveries. And I'm going to say xi is the number of runs scored in the ith delivery. Okay. So you have now 6 random variables. And what can we possibly say about these 6 random variables? Okay. So you have xi I equals 1 to 6. Okay. What kind of values will xi take? What are the numbers that can be scored of one delivery in cricket? People might say 0, 1, 2, 3 is possible, 4 is possible. Is 5 possible? Yeah, I know it can be a no ball and a 4. 6 is possible. Is 7 possible? 7 is possible. Let's just say 8 is also possible. You can go and look at the history of cricket. I think there's not really been a serious match in the modern era where more than 8 runs have been scored of one delivery. Okay, 7 is possible because of a no ball you can hit a 6 and you get 7. But 8 is very difficult, you know. I mean, you need to get an overthrow 4 after you run 4 runs. It can happen. It's very, very, very rare. Okay. But you can go look up cricket, modern day cricket. This is it. I mean, beyond 8 is, I think, for most practical purposes, unreasonable. If you think it's possible, you can put in the 8 also, 9 also. Okay, so every random variable here, x1 through x6, takes this one of 9 possibilities. And what do you think will be the joint distribution? Okay, joint PMF. Okay. So if you think of the joint PMF, let's say you want to think of fx1, x2, x3, x4, x5, x6. I mean, even writing it down is laborious, isn't it? Of let's say 0, 1, 5, 4, 2, 0, 0. Okay. So what is the probability of this? How does one even do something like this, right? It's not even clear how in a power play over one can decide something like this. What's the probability of a maiden over, right? So that's like f all of this of 0, 0, 0, 0, 0. So it seems fairly confusing as to what to even do in these kind of problems. How do you think of the joint PMF? And it seems quite extensive. I mean, if you just think of the number of possibilities for all of these guys, it seems like it's 8 power 6. Okay. This is just too many possibilities, and even to write it down and think about it is really, really hard, isn't it? So this is very typical of modern data problems, and the vastness of what is possible, and and what you can measure or what you can reasonably say is very limited, and you have to try and do something with that kind of situation. Okay, so this is very common in modern problems. Sometimes the data is vast, but sometimes data is not vast. So you have to think about how to deal with it. But even if the data were there, even if somebody were to give you the probabilities, it is just a huge thing to define. You have to define so many things to define the joint PMF, right? It's not as simple as even the previous problem. Okay. Anyway, so I just wanted to put this out there for you to think about how more complicated real scenarios can be, and to write down precise probabilistic things is very tough. So we need some tools to think of such joint PMFs in simple ways. Okay, and that's where this marginalization and conditioning will help you. Okay, so quite often in practice, when you have big complicated scenarios like this, people always think in terms of marginal distributions and conditional distributions. The joint PMF itself might be too unwieldy to write down, so you think of how marginalization and conditional PMFs will work, and that's a very important part, and that will come in the next lecture. Okay, so we'll see that in the next lecture.